Okay, good morning. So this is our 36th lecture, and in the previous lecture we have completed our discussion on the linearized subsonic flow. So today we will try to take up the discussion on linearized supersonic flow. Okay. So the very first point is, in case of subsonic flow, if you remember, our equation was beta times beta square times phi xx plus phi yy equal to 0. Okay, so this was the equation. Now here beta was nothing but square root of 1 minus m infinity square, and we know that for subsonic flow Mach number is less than 1, so that's why this value was coming as positive. Okay, but when you will be going for the supersonic flow situation, then ultimately what will be happening, our Mach number m infinity will be greater than 1, and if you keep this equation in this form only, then we will be getting nothing but the non-real number over here. Okay, so what we will be doing, we will be multiplying this equation with minus sign. So if I do so then ultimately I get my equation as lambda square times phi xx minus phi yy equal to 0. So this equation is applicable for now supersonic flow, provided that lambda is equal to square of m infinity square minus 1. Okay, so that is the thing. Actually for supersonic flow, equation will take this particular form. Okay. Now what we have to do, we have this equation. Now we can take any thin slender object, okay, and over that thin slender object actually we can try to solve this particular equation. That will be my linearized solution for a supersonic flow. Okay, so let's consider that we have some bump over here in the flow. So this is symmetric shape, something like this. Okay, so this is a bump over here. Now when the streamline will come, so this will slightly deviate, and here I will be getting some local components of velocity. Okay, and ultimately our interest is to determine coefficient of drag and coefficient of lift, coefficient of pressure, etc. for this. So once we are able to calculate coefficient of pressure, then others will be obviously are related, so we will be able to find others as well. Okay, so main interest is to find out the coefficient of pressure. So if I consider this situation, and if I consider that my free stream Mach number over here is greater than 5, so that is means our flow is nothing, free stream Mach number is greater than 1.2. okay, so it means it is nothing but my supersonic flow. Okay, so for this supersonic flow situation, if you see, our equation is, I have written in the previous slide, lambda square phi xx minus phi yy equal to 0. Do you see any familiarity of this equation with any equation that we studied earlier? If you recall, earlier we have studied the linearized acoustic waves. Okay, what was the wave equation? Phi xx equal to c square times phi tt. That was the wave equation. Okay, and this particular equation is also like this. So if you just replace t with the x, then what you are having? So there, in that acoustic wave case, we were having one spatial parameter and one time parameter. Over here we are having a two-dimensional flow situation, so we are having two spatial parameters. Is this point clear? So it means this equation is nothing but identical to that of a 1D wave equation. And if you see, so we need not to now go into the detailed solution of this, because already we have seen the detailed solution of 1D wave equation is f of x minus ct plus g of x plus ct. So that was the solution. Okay, so over here also phi of xy will become say some function f of x minus lambda y plus g of some function x plus lambda y. Okay, so that this analogy we are taking from our earlier lecture where when we have studied the linearized acoustic waves. Okay, so in case of linearized acoustic waves we have studied this particular concept. Now ultimately what will be happening, so this is my equation. So now one thing I can do, first I can assume that g of x plus lambda y is equal to 0. Okay, so in that case what I will be having, I will be having phi of xy equal to f of x minus lambda y. Okay, now let's consider that my interest is to plot the isophi lines. It means that phi line over this flow field along which the value of phi is remaining constant. Okay, so if I want to plot the constant phi lines, then I can say that say my phi of xy equal to f of x minus lambda y, which is equal to constant. So some constant value of phi I want to obtain. Okay, so I will be getting value of phi as constant if my argument to the function x minus lambda y is also constant. Okay, so if function is f is a function of x minus lambda y, so this argument has to be constant, then only this function will be giving me a fixed value. So that is the reason I will be putting for constant value of phi x minus lambda y is equal to 0. And from here if I do d by dx of this equation, so that will be becoming d by dx of x minus lambda y equal to sorry, not 0, this has to be constant. Okay, so this will be d by dx of constant. So ultimately I will be getting 1 minus lambda dy by dx equal to 0, and from here dy by dx equal to 1 by lambda, which is nothing but equal to 1 divided by m infinity square minus 1. Fine. Is this point clear? So it means that, and you might be surprised that if you see a Mach wave, for a Mach wave, value of Mach wave angle mu, that is nothing but equal to sine inverse 1 by m infinity, 1 by Mach number. Okay, and that can be written as, in terms of tan theta, that can be written as tan inverse of 1 by m infinity square minus 1. So ultimately the point is this dy by dx whatever I am getting over here, this is nothing but coming equal to, this is coming equal to Mach angle, tan of Mach angle mu. Fine. Is this point clear? So it means that whatever the waves or isophi lines will be producing over this surface, these isophi lines will be nothing but identical to weak Mach waves. Is this point clear? So now if I plot any isophi line over here, so you can see dy by dx is 1 by m infinity square minus 1. So slope of that dy by dx will be 1 by lambda, and ultimately that is nothing but equal to tan theta of mu. So if I plot any line over here, so these are the lines. Okay, and slope of this line is nothing but equal to 1 by lambda, and this is also equal to tan of mu. So it means this angle with the free stream direction is nothing but mu. Is this point clear? So this angle with the free stream direction is mu. So ultimately for this reason my g function is nothing but equal to 0. So here what we have done, we have considered that g function is equal to 0. Is this point clear? Now what will be happening? So from the bottom region, so let's consider that for the bottom region, let's consider that our f equal to 0. So in that case, I will be getting phi xy is nothing but equal to g times of x plus lambda y. And from here, if you calculate, then dy by dx will be minus 1 by lambda. Okay, so it means slope will be negative. Okay, slope will be negative. So in bottom region, if I plot, then it has to go in the negative slope direction. So line will be something like this. Okay, so one side we have left running waves, one side we have right running waves. Okay, and here f is equal to 0, and this slope of the line is minus 1 by lambda. Is this point clear? So one side we have, as I told you, one side we have nothing but left running wave, one side we have right running wave. Okay. So typically you can see that in case of a supersonic flow, the isophi lines, okay, the lines where velocity potential function is constant, these lines are coinciding with nothing but the weak Mach waves. Okay. So ultimately over here, we are not talking about the waves. When we are considering the linearized theory, we have not considered that shock wave is forming here or there. Okay, but ultimately what we are considering the solution of phi, and that solution of phi is coming in such a way that the isophi lines are actually coinciding with the Mach waves, if we just make the analogy. Okay, but here we are not talking about the waves. Okay, shock wave, we have not said that we have any shock wave over here. Obviously physically there will be, but linearized theory is not accounting for the shock wave. Okay, over here into our mathematical analysis, by using linearized theory, we are not accounting for the shock wave, because shock wave phenomenon is a non-linear one. Okay, so you can see over here that just by solving for the linearized velocity potential equation, we are able to somehow include the effect of the shock wave. Okay, ultimately also you will see how later on in value of Cp how this effect is coming. So up to this point, is it clear? Up to this point, is it clear? So now our interest is to calculate the value of U, because what is the definition of Cp? From linearized theory, our pressure coefficient is minus 2 Vx dash by V infinity. So our interest is now to calculate the value of Vx dash. Okay, so Vx dash will be del phi by del x. Okay, so ultimately say when I have used this formulation that g is 0, corresponding to that I will get del by del x minus lambda y into f of x minus lambda y into del by del x of x minus lambda y. Okay, so ultimately I will get, say, f dash over here, because this will be equal to 1. Okay, so this is my Vx dash. Now let's also calculate Vy dash. So if I calculate Vy dash, that will be del phi by del y, and that will become equal to f dash time. So this will be same, and here I will be having del by del y of this. So f dash time minus of lambda. Okay, now let's substitute f dash from the previous one. So I will be getting Vy dash equal to minus of Vx dash into lambda, and from here my Vx dash is equal to Vy dash by lambda. Is this point clear? So minus of Vy dash by lambda. So this is one relation we have got. Okay, another relation we can got nothing but from the geometry of the problem. Okay, how geometry of the problem? So you know that we have done previously also. If this curve is given by y equal to f of x, then ultimately the slope of the tangent to this curve at any point, tangent to this curve will give me, say, angle theta. So tan of theta will be nothing but equal to from previous lecture, have you forgot? Dy by dx, okay, at any point on the wall will be equal to tan of theta, okay, and that will be equal to, this is my velocity vector, it will be having two components, v infinity plus vx dash, and this component will be vy dash. So what will be tan theta? Vy dash upon v infinity plus, okay, so this is from the previous lecture, okay. So from the geometric conditions at the wall, we will be getting this particular one, okay. So now if I consider that I have small perturbation, so because we are talking about small perturbation, so ultimately vx dash will be very small than v infinity, and theta will also be small because perturbation in the flow is small. So for that case I can simply say that tan theta is nearly equal to theta. So theta will be equal to vy dash by v infinity, okay. And ultimately what I will get? I will get that vy dash is equal to v infinity into theta. So let me substitute this value of vy dash in the previous equation. So what I will get then? Then I will get vx dash is equal to minus vy dash by lambda. So vy dash has become v infinity into theta by lambda. So if this is the case, then I can find out the value of Cp. So value of Cp will become minus 2 v x dash by v infinity. So minus minus will cancel, v infinity will cancel. I will get 2 times of theta divided by lambda. So ultimately Cp will be equal to 2 theta by m infinity square minus 1 and square root of this. Is this one clear? So this is my value of Cp for a supersonic linearized flow. So I will be calling this as nothing but linearized pressure coefficient, and this linearized pressure coefficient is for supersonic flow, okay. So this linearized pressure coefficient is for supersonic flow. Now let's relate it physically. So let's consider that I have one biconvex aerofoil. Okay, so this is nothing but symmetric biconvex aerofoil, okay. Now say I have some points on this aerofoil. Here I have point A, here I have point B, then C, and then D. So at point A, say the slope is this, so angle is theta A. At point B, slope will be this, so angle will be theta B. Okay. So now if you want to calculate the value of Cp at point A, so Cp at A will be equal to 2 theta A by m infinity square minus 1, and Cp at point B will be equal to 2 theta B by m infinity square minus 1, okay. So if you see, this theta A over here is from the direction of the free stream. If I measure this theta, it is coming in anti-clockwise direction, so which is a positive direction. So this theta A will be having positive value. On the other hand, if you measure theta B, it is coming in the clockwise direction from the direction of the free stream, okay. So it means that theta B will be having negative value, okay. So the meaning is, if you plot the value of Cp for this aerofoil, okay, so in initial portion Cp will be positive, and then in the other half it will be negative. Is this point clear? So this is positive, this is negative. Okay. Point is clear? Similarly, if you go to point C and D, so when we will be calculating the CP for point C and D, then we have to do the calculation that F equal to 0, because bottom portion F will be equal to 0 and G will be, we will be having finite. So then in that case we are having nothing but x plus lambda y equal to 0. So when we will be going with this plus sign over here, ultimately I will be finding that for bottom portion my CP formulation will be minus 2 theta by m infinity square minus 1. Is this point clear? So when, if you calculate for the bottom portion, then value of CP should be minus 2 theta. Now you can verify also over here. So if you take this angle, so this angle theta C will be negative and this angle theta D will be positive. So ultimately this positive will make negative CP on D point, and this negative angle will make positive on this side. And this is making correlation with the theory also. So from theoretical understanding we know that here pressure will be acting in positive x direction. So here CP should be positive. On the back end pressure will be acting in negative direction. So here my area vector and pressure vector will be in opposite direction, outward normal and pressure. So that's why CP value should be negative. So it is making relation with theory also. So mathematically also we are getting this and theories. So you need not to remember the sign over here. The point is very clear. If pressure and outward normal are in the same direction, then it is a depending upon the physical principle. So you can say in positive direction it will create force on this side, here it will create force on this side. So depending upon that you can actually choose the value over here. Okay. Now interesting point is that here CP value is positive and here CP value is negative. So ultimately when you will be calculating the drag force, okay, so this minus minus will become positive and ultimately we will be getting over here nothing but a finite drag force. In case of subsonic flow, what was happening? Pressure CP was having same sign on both the ends. Okay, as CP was having same sign on both the ends, then actually our CP was cancelling both the sides. So if CP was cancelling both the sides, so both the sides pressure was cancelling each other. So that is the reason that we were having nothing but a zero drag force. Okay, but over here because one is positive, one is negative, so when you will be calculating the net balance, that will be giving us a finite drag force. Okay, and this particular drag force which is coming on this body, that is called as nothing but the wave drag. So we know that in case of supersonic flow, in case of subsonic flow there is no shock wave, but in case of supersonic flow shock wave comes, shock wave alters the flow field and ultimately it causes a positive drag which is called as wave drag. So that is the reason that though in our linearized theory nowhere we have talked about the shock wave, but still ultimately whatever the value of CP we are getting, that value of CP is actually giving us nothing but the finite drag which is called as the wave drag over here. Okay, now interestingly, so is this point clear? Now if we compare the value of pressure coefficient as function of Mach number for subsonic and supersonic region, what we will be getting? Say this is my Mach number m infinity equal to 1. So before this I will be having subsonic flow and above this I will be having supersonic flow. Okay. So if you see earlier we have Prandtl-Gloret rule. So if from the parental rule I see the value of Cp, that is inversely proportional to 1 minus m infinity square. Okay, and here I have got Cp as inversely proportional to m infinity square minus 1. So ultimately what will be happening in this region, when Mach number is increasing, value of Cp will increase for the subsonic region. And ultimately at Mach number equal to 1 it will be undefined, so that's why we will be having some asymptotic line over here. Okay, similarly here what will be happening in supersonic region, I will be finding that value of Cp will keep on decreasing when we are increasing the Mach number. Okay, is this point clear? So this is one important point. Then after this, if you recall in the previous class, I have taken one specific shape, one wavy surface I have taken, such that if h is its amplitude and lambda is wavelength, then I consider that h by lambda is very smaller than 1. And for this wavy surface, we have applied the linearized subsonic theory, and then we tried to predict the value of Cp and other parameters. Okay. So what I suggest, this is if I consider now in place of subsonic, if I consider supersonic flow over this. Okay. So say m infinity is greater than 1. So if I consider supersonic flow over this, then ultimately and h by lambda is very smaller than 1. So then it becomes a case of a supersonic flow. Okay, so for the supersonic flow solution, we already know that phi xy will be equal to f of x minus lambda y plus g of x plus lambda y. The only thing you have to do is, the way I have substituted these boundary conditions for this hump structure. Okay, in the similar way you have to substitute the boundary conditions for this wavy profile. Okay, and once you substitute the boundary conditions over this wavy profile, and what are the boundary conditions, that I have already told you in the previous lecture. So if you substitute boundary conditions, you will be able to, just a moment, yeah, it has come. Okay, so now if you substitute the boundary conditions, you will be able to calculate the values of f and g. Okay, so this is example problem 9.2 in your textbook. So I suggest all of you go through this. I will not going to repeat it because already I have given you the general solution. You have to simply substitute the boundary conditions which I have discussed in the previous lecture, and then you have to find out these derivatives and ultimately calculate the value of f and g to find out Cp. Is this point clear? Okay, so this you can actually do by your own. This is, and for reference, whether if you are doing correct or not, you can check example number 9.2 from your textbook. Okay, okay. Now comes one important concept which is called as the concept of critical Mach number. Okay, so what is critical Mach number? Say I have aerofoil like this. Here say I have free stream flow, I will be having some value of m infinity. I know that in the top portion what happens, flow actually accelerates. Okay, so when flow will be accelerating, my local Mach number will be increasing. Okay, so on this aerofoil, say this point is point number A, which is the point corresponding to the maximum acceleration of the flow. So if this is the point corresponding to maximum acceleration of the flow, at this point only my local Mach number will be highest. Okay, so value of local Mach number at point A will be highest if this is the point of maximum acceleration of the flow. Okay, so now there is this thing. So if my m infinity is equal to 0.3, then corresponding to this I will be finding that local Mach number at point A is nothing but 0.435. Okay, if my m infinity is equal to 0.5, corresponding to that ma will be 0.772. Okay, if my m infinity is equal to 0.61, then I will be getting ma equal to 1.0. Okay, so when at point 1 my local Mach number has become supersonic. Now if I increase m infinity above than 0.61, then what will be happening? Here I will be getting some finite region of the supersonic flow. Okay, and once I have supersonic flow, then ultimately here I will be getting a shock wave also. Okay, so ultimately what happens, if I increase m infinity greater than 0.61, then my Mach number beyond point A can go above than 1. So if it is going above than 1, then I will be getting some finite region over here where I will be having nothing but the supersonic flow. So as I have supersonic flow over here, so when I am having transition from supersonic to subsonic flow, at that transition I must have a shock wave. So here I will be finding that there will be formation of a weak shock wave. Okay, here I will be having formation of a weak shock wave, and whenever I have the formation of a shock wave, ultimately what will happen? This shock wave will increase the pressure in the downstream. If pressure is increasing in the downstream, I will be getting the case of nothing but a adverse pressure gradient on the downstream of the shock wave. So I will be having the case of adverse pressure gradient. If I have the adverse pressure gradient, then in real life situation, when viscosity is also playing a role, so in real life situation what I will be finding? I will be finding that there will be boundary layer separation. Okay, so in real situation I will be having nothing but the boundary layer separation. Okay, so this boundary layer separation, what it does, it increases the drag force by significant amount. Okay, there will be significantly high increase in the drag force, and this significant high increase in the drag force decreases the lift force, and then you may find that in this portion lift is very small, whereas in the tail end lift is significant. That can create some movement over here which can even topple the aeroplane. Okay, so ultimately what we see that the condition corresponding to which my Mach number is becoming equal to 1 at the point of maximum acceleration, that particular Mach number I call as MCR, which is called as critical Mach number. So the meaning is, if I am operating in a subsonic regime, for a subsonic aeroplane, what I have to do, I should not increase the Mach number value above than critical Mach number. Okay, if I increase above than critical Mach number, then there will be this mixed finite sized supersonic subsonic regime, which will lead to the adverse effects. Okay, so ultimately if I want to translate this in terms of the so is this point first clear? What is critical Mach number? Now if I want to translate this in terms of the drag force, then it comes something like this. If I plot CD, drag force coefficient, as function of m infinity, so what I will be finding, that when my Mach number is very low, then drag coefficient will remain constant. Okay, up to certain point, say this is my point A, where my Mach number is equal to M critical. If I go slightly above this Mach number, then also there will not be much change in the drag force. Okay, but if I reach at point B, okay, which is slightly above than critical, having this one finite deviation from the critical Mach number. If I go to free stream Mach number at this point, then after this point I will be finding that there will be significant increase in the drag coefficient. So it means here drag force was very small. Now you can see the drag force has increased by significant amount, and there is sudden increase in the drag force. So basically this point V, the Mach number corresponding to point V, is called as drag divergence Mach number. Okay, so this is called as drag divergence Mach number. Now for any aerodynamic object, our interest is to have the value of this drag divergence Mach number as low as possible. This is our interest. Okay, so if you are having aerodynamic body, you want to make aerodynamic body in such a way so that our drag divergence Mach number is actually small. Sorry, drag divergence Mach number is large. Okay, so how this can be understood with better clarity? So let's consider that. So what I want that this drag divergence Mach number should be large. If drag divergence Mach number is large, then I can keep my M infinity value as large. Okay, if it is small, then M infinity has to be also small. Okay, so how to find out exactly the value of what will be the drag divergence Mach number corresponding to some situation, that I can actually find out. So yeah, this is the situation. So if you calculate the ratio of P by PA or P infinity by PA, so P infinity means I should calculate in other way. Say I want to calculate PA by P infinity. Okay, because if you see, one definition of CP for compressible flow is also 2 by gamma M infinity square into P by P infinity minus 1. This is also one definition. Okay, so if I want to calculate the value of Cp at point A, I must calculate Pa by P infinity. So Pa by P infinity, if you recall from our earlier shock wave theory, okay, chapter number 3 or 4, okay, so very initial analysis. So for the normal shock wave cases, we have seen that Pa by P infinity can be related as 1 plus gamma minus 1 by 2 M infinity square divided by 1 plus gamma minus 1 by 2 M A square whole power gamma by gamma minus 1. So if I substitute this over here, then I can calculate the value of CPA. So CPA will be equal to 2 by gamma M infinity square into 1 plus gamma minus 1 by 2 M infinity square divided by 1 plus gamma minus 1 by 2 M A square, and this power gamma by gamma minus 1 minus of 1. So this is my CPA over here. Okay. Now if I take the special case that I have free stream Mach number is nothing but equal to critical Mach number. So if my M infinity is equal to M critical, okay, then corresponding to that MA will be equal to, if M infinity is M critical, then what will be the value of MA? Just now I have explained you. So when M infinity is M critical, then MA is equal to 1. Let's substitute this over here. So if I substitute, then what I will be getting? I will be getting CPA, and this is corresponding to critical pressure coefficient. So critical pressure coefficient will become 2 by gamma M critical square into 1 plus gamma minus 1 by 2 m infinity square divided by 1 plus gamma minus 1 by 2 whole power gamma by gamma minus 1 minus of 1. Sorry, this m infinity will also become m critical. So now if you see, this particular equation is a sole function of Mach number, because gamma for a particular medium will be constant. So now this equation has become a sole function of a Mach number. So if I plot this equation with Mach number, if I plot this equation with Mach number, then Cp as function of m infinity will be becoming, so this is the solution of this equation will come something like this on this curve. So this is my Cp critical solution. Okay. And for subsonic flow situation, just now we have seen from Prandtl-Gloret rule or any other rule, okay, like Karman-Tyson rule, if we calculate the value of Cp, that varies something like this with Mach number. Okay, so this is coming from, say, Prandtl linearized pressure coefficient. Okay, so the point where these two are intersecting, that point will be nothing but my critical Mach number, because this is the equation of a critical flow and this is the situation of a actual subsonic. So where these two will be intersecting, that will be point of a. So say this is for some so if I have aerofoil, then in case of aerofoil we have two important parameters. One is the point of maximum thickness is given by T, and then this length from this point to this point is called as chord length, and T by C is the important parameter. Okay, so say this is for some smaller value of T by C. If you increase the thickness of the aerofoil, what will be happening? Upon increasing the thickness, our Cp value will increase. So if you increase the thickness, then your curve will shift something like this. If more thickness, then curve will shift like this. So it means that when you are increasing the thickness of the aerofoil, your critical Mach number is going down. Is this point clear? So upon increasing the thickness of the aerofoil, whatever the critical Mach number, corresponding to which Mach number becomes 1 at the point of maximum acceleration, the value of that Mach number is actually going down. Okay, this can also be seen with the help of this curve. So people have performed experiments and then found drag coefficient, and this drag coefficient is represented as function of m infinity, and it was found that if this is the curve for some higher thickness aerofoil, then this curve goes something like this for slightly lower thickness aerofoil, and even it bends more down and something like this for even more thickness, less thickness aerofoil. So say here T by C is equal to 9%, here T by C is 6%, and here T by C is say 4%. So as you are increasing, as you are decreasing the thickness, okay, then earlier this was the critical Mach number for this thickness. Now this is the, sorry, not critical, this is the drag divergence Mach number. Now this is the drag divergence Mach number, and now this is the drag divergence Mach number. So when you are decreasing the thickness, your drag divergence Mach number is actually increasing. So it means one way of achieving high speed flows, what we want our aeroplane to move at high speed. If we want aeroplane to move at high speed, then corresponding to that our critical Mach number should be large, then only I can achieve the free stream Mach number also large. Okay, so it means in order to achieve the high speed flow, our aerofoil should be thin. Okay, so aerofoil should be thin. Second strategy which is generally followed, that is called as the swept aerofoil structure. So what is basically done, the shape of the aerofoil is actually swept in backward direction through some angle. Okay, so generally let's consider that this is my cross-sectional view of the aerofoil, and say this is point of maximum thickness, and say this T1 by C1. So this point from here to here is nothing but my C1, and this point of T1 by C1 is equal to say 0.15, and corresponding to this, say if I see the plane view, then this is my aerofoil, straight blades. Okay, and when you will be finding a flow streamline is coming, so flow streamline will approach and that will go something like this. Now if you do sweeping of the aerofoil structure in the backward direction, so then what will be happening, say this is the point where aerofoil is starting and you have taken shape something like this. Say this is at some theta angle, this is swept in the backward direction. Now if you plot with reference to the streamline, so say streamline will be entering something like this. Okay, now with reference to the streamline, if you plot the this view of the aerofoil, so what you will be finding, you will be finding that aerofoil is say starting at this point, having same thickness but ending at this point. So now because thickness of the aerofoil we are not changing, so T1 is equal to T2 only, but we have just changed the angle. So corresponding to that, whatever my new chord length C2 we will be having, that will be larger in comparison to C1, and we will be experiencing with this angle relation, if theta is equal to 45 degree, then C2 will be 1.41 times of C1. If this is the case, then I will be finding that T2 by C2 will be smaller than T1 by C1. So by just sweeping the aerofoil through certain angle, the flow is finding that T by C ratio is small. Okay, so it means aerofoil with straight blade was appearing thick for the flow, but for the same flow, aerofoil with tilted sweeping in backward direction, that is appearing as thin for the same flow situation. So it means this way also I can increase nothing but the Mach number. Okay, so if you want to see that is the reason that blades, this aerofoil structure of an aeroplane is actually not straight. So if you see from the top view aeroplane, how it looks like. Say this is the main central portion. Then if you see the aerofoil, then it is something like this. So from the front, it is not straight. Okay, it is like this. Because this type of sweeping actually increases the critical Mach number which is required. Okay, so we are not going to very much details of this. If you are interested, you can even, maybe for aerospace people this may be of more interest, which is who are interested in flight mechanics, etc. So there ultimately there are other reasoning is also that when the flow enters over here, then some part of the flow goes in this direction, then in this direction flow remains less, so that way initial free stream Mach number. So there are different things, so that if someone is interested in flight mechanics, then you can go into more details. Okay, but from the understanding of compressible flow, we can say that if thickness by chord ratio we are able to maintain thin, then ultimately our drag divergence Mach number value will become large. So if that value is becoming large, then I can have my free stream Mach number larger. Okay, so that is the understanding. If you see, this structure was proposed by Adolf Busemann, and this was proposed in uh, somewhere in, actually, I think 1935 or 1940, something like that, nearly in 1940. Okay, the first, I have given you one example of a very first supersonic aircraft, Bell XS-1. Okay, so Bell XS-1 was in 1944. At that time, that supersonic aircraft was not having this type of sweeping. Okay, so Bell XX1 was having straight blades at that time. But how they achieved the stability in Bell XS1? The thickness of the Bell XS1 aerofoil was very, very small. But later on, when they have got the more advanced versions of Bell XS1, for example, Bell XS5, that was having sweep blades and with slightly more thicker in comparison to this one. Okay, so the reason was because by that time this particular theory was not much developed, but still Adolf Busemann was the one who has given this type of velocity triangles for sweeping sweep aerofoil structure, and he has proposed that by using this type of structure we can actually have higher drag divergence Mach number. Okay. So this is all about linearized flow theory. Now we have one more thing in terms of potential flow analysis. If you recall earlier, I have given you I have told you while we studied the two-dimensional flow over the wedges, then I told you that when we study the flow over a cone, then actually it is of three-dimensional nature. Okay, so ultimately this cone flow, if we solve in cylindrical coordinate system, then actually it can be considered as quasi two-dimensional flow or axisymmetric flow. Okay, so we will try to do the non-linear conical flow solution now. So maybe not in today's lecture. Today I will just brief about some key features of the conical flow, and then in the next lecture we will do the derivation. Okay, so let's talk about conical flows. First point is why conical flows are important. So if you see the nose of high-speed missiles, high-speed aeroplanes, okay, or other high-speed aerodynamic object, you will be finding from the top, nose is just pointed and then it is gradually expanding like a cone. Okay, so almost all the high-speed aerodynamic objects are having their leading edge which is penetrating into the flow in the form of a cone only. Okay, and a conical structure, if I see from the side view, so side view it will be, say this is my z axis and this is my radial axis r. So from the side view I can say that if I have any planar geometry over here, if I rotate this planar geometry over 3 dimensions, then that will be becoming a cone. Okay, and a 3-dimensional perspective view of this will be something like this. Say this is my z, this is r. So now I can say that I have a conical structure something like this, and here I have variation in the angular direction phi. Fine. Now when the flow will be happening over, so importance I have already told you that it is found in many, it is basically main thing which is penetrating into the flow, so that is of conical shape in majority of the aerodynamic objects. Okay, so typically if you see a conical cone will be something like this, it will be represented something like this. So say I have one infinite cone, so it means it is extending up to infinity in this direction. Okay, and say I have over here some flow which is happening over this, and this flow is actually supersonic, so Mach number over here is greater than 1. So if I have this situation, what I will be finding that here I will be having the formation of a shock wave. So here I will be having a shock. Now one interesting feature is, if I just visualize the streamline of a conical flow, then I will be finding that here it will be suddenly changing its direction. Okay, there will be discontinuous change in its direction. But in case of wedge flow, what we have seen, if I talk about just a two-dimensional wedge flow, there we have seen that if here I am having a shock wave, this discontinuity will be immediately make my streamline parallel to the wedge. But here this does not happen. Here, though, in case of conical flow, as I told you, I have some sudden change in streamline flow, but it is not immediately becoming parallel to the surface of the cone. What will be happening? First, I am having sudden discontinuity, and then it will be taking some gradual asymptotic transition before it becomes parallel to the surface of the cone. Okay. So this is something which is people have tested, and these are the experimental evidence. Okay, so experimentally people have observed that in case of a two-dimensional wedge flow, what happens? Immediately the streamline adjusts parallel to the surface. But in case of a conical flow, this does not happen, and streamline here it suddenly changes, and after that it gradually rotates before it becomes parallel to the surface. Okay, so one important point happens over here. So say if I take one assumption that pressure, because of this bend of the streamline, if pressure at different points on the surface of the aerofoil of this conical plane is different, then actually we will be finding that analysis become very complex. So one assumption we introduce to the analysis is that over this surface pressure and all the flow properties are constant. Okay, and ultimately what we find that this surface can be considered as nothing but, if this is my vertex, say if I put a light source over here, from this light source some ray will go like this along the surface. So that ray I can consider nothing but a constant property line if I assume constant properties on the surface. Similarly, if I put a light source that will be emitting multiple rays, so I can have one more ray over here, something like this, then I can have one more ray over here, something like this. So what generally we do in case of conical flow, we say that all these rays are nothing but the lines where our pressure, temperature, density, velocity, etc. are constant. So these rays are nothing but of constant property lines. However, from one ray to other ray, we will be having variation in the property. Okay, so this is something which people have observed experimentally, and they are having experimental evidences for the same. And one important thing which we will be doing in our analysis, because shape of the cone is axisymmetric, so in the azimuthal direction, so when our phi is actually changing, in that direction we will not be experiencing any change. Okay, so ultimately del by del phi of any quantity will be 0 for the conical flow situation whenever we will try to find out the solution of this. Okay, is this point clear? So the important point is, somewhere in 1929, for the first time the conical flow solution was once again given by Adolf Busemann. But that solution was not mathematical. He has given the solution in the form of graphical representation. So he has given the graphical solution of the supersonic flow over a cone. And by that time, if you see the supersonic flow from our history lecture, initial lecture, supersonic flow has become matured after World War II. So by that time, people were not even knowing much about the supersonic flow, and he has given graphical solution at that time. And later on, in the year 1935, Taylor and McCall, they have actually given the mathematical solution. So in the next lecture, whatever solution we will try to see for this conical flow problem, so that will be basically taken from the Taylor and McCall's solution, which they have provided in 1935. Okay, are you able to understand this point, what I have explained in terms of ray? Okay, so say if you have a light source, then you will be having spectrum of rays. So one spectrum of ray which is going, and this spectrum if you rotate, so say this is the ray, if you rotate this ray and make another conical envelope for that particular value of phi, okay, you will be finding that along that complete envelope your properties are constant. Then if you just change the phi to another value, sorry, not phi, if you change the ray to another angle, okay, then you will be finding one more envelope. Over that another envelope also properties will be constant, but the properties will be different from one envelope to another envelope when we are traveling. Okay, is this point clear? In two-dimensional representation, that is looking as nothing but a single ray, because in angular direction there is no variation, so whatever the property value over here is, same will be property value in the complete 360-degree rotation of that. So you can consider that the whole surface of the cone is having same value of the properties. Then outside that you can take another envelope, in that also there is constant value of property, then another neighboring envelope, so likewise your property variation will be traveling from one envelope to another envelope, but within a single envelope, because in angular direction variation is not there, properties will remain the constant. Okay, so these are something which are initially, these theories were taken from the initial experimental evidences. So first initial experimental evidence was there, and then this type of assumptions were introduced. So we will see detailed mathematical solution in the next lecture. Now I'll stop at this point.